Hey there. So today we will implement Quicksort. In the last video we implemented bottom-up merge sort, and I hope you understood it. And if not, no worries. I'm always there to answer your queries. But today we are going to implement Quicksort, and Quicksort is really the quickest sorting algorithm out there. It is an in-place algorithm so that you don't have to create extra memory like we did in case of merge sort. We were creating auxiliary and we were copying the array afterwards. But in Quicksort, we don't do anything of that sort. It's really, I won't say it's simple, because when I was in college, I had a hard time understanding it. Then I had to read a lot, and then finally I landed on a video by Robert Sedgewick. And the way he explained Quicksort, I mean, amazing. I never forget it afterwards. And I'm going to teach the same way that I learned it. And before we jump to code, I want you to understand on this, and I really emphasize on this point, that the pivot in Quicksort is really important, and you need to understand the basis of the pivot. So in each iteration, we select a pivot, and then we place the pivot in its correct position. And by correct position is that everything on the right of the pivot is bigger than this number, and everything on the left of the pivot is smaller than this number. And this is kind of an important point, because this is the way it sorts. So once in the first iteration, you will pick the pivot, you will place it in the right position. Now you have two halves, one that is smaller than the pivot, other one which is bigger than the pivot. And then you do sort these two parts recursively by divide and conquer again. So you just continue the process again and again. You will find a pivot in this part, then you will place it in the correct position. Then the right of that will be bigger, the left will be smaller, and you will sort it. And at the end, you get a sorted array. That's the whole crux of it. And just keep this in mind when we will write code, because this is the essence of it all. That's all. I mean, Quicksort is really easy to implement. I mean, even easier than merge sort, and it is way faster than it. Like, if you can implement it correctly, it can be 2 or 3 times faster than heap sort, and I think twice faster than merge sort. Then there are other ways you can optimize this algorithm, like 2-way quicksort, then there's 3-way quicksort. So I mean, the possibilities are immense, and you're going to learn a lot from this. I mean, in interview also, people ask question which has a part implementation of this algorithm. So if you're going to learn it, this is going to help you big time. So yeah, enough talking. Let's head back to our IDE and code. And I really do believe that the best way to learn any algorithm is via code. So once you're done with the theory, always implement it and learn it. So yeah, see you there. Hey, so this is where we left off last time. We implemented bottom-up merge sort. So today we will create Quicksort. We'll implement Quicksort. So as usual, we'll create the class, we'll implement the sort interface. This will give us a sort method. Then we'll create a test class. Today I'm not able to speak that well, really tired by the way. But anyway, I love this coding, so it's my hobby. We paste it here. We change this to our testing class, which is Quicksort, and we will run it once to see that, okay, our test and everything is working the way we want it to work. Cool. Our test case failed for the first time. I'll close these tabs. So this is where we will do our Quicksort. So I'll quickly copy this array into a new one so that I do not change the input by mistake. We'll always create a new array and we'll perform operations on that. Now, in Quicksort, I mean, we deal with the pivot as I explained you. So we are going to do the same thing. So first of all, in the first iteration, we have the entire array to find, and we have to find the pivot in the entire array. So we need a start index, which will be 0. Then we need a end index, which is the length of the array. Then we'll create a method called Quicksort, and we'll pass in the array, the start index and the end index. And at the end, once that method is complete, then we'll pass the array back to the caller, and this array should be sorted here. So let's create this method. Awesome. So since we are going to call this method recursively, and whenever you do a recursive call, you should start with the end condition in mind. And here the end condition is, if my start is gonna be equal to my end, I'm gonna return it. So now I'm pretty sure that it won't stuck in the infinite loop, and it won't give me a a Stack Overflow error or something like that. I'm safe here if I implement it correctly. Cool. So once I have this, now I need to choose a pivot. So choose a pivot. And there are different ways of choosing a pivot, but here we are going to choose it randomly, which gives us a pretty decent runtime. And to choose a random number, we'll create a random object. So easy. Then we'll call next int. Now this will give me a number, but I need to make sure that it is in bounds. In bounds is it should be between start and end. It shouldn't be any number. So for that we can do end minus start. This will always give me a number which is in limit, but it could be like anywhere around. So I'll bring it in limit. Let's say I get, this is my original array, but I am somewhere in this array. So I want a number which is between this. I don't want a number which is here, right? So for that, I'm going to add my start position to it. So this will give me a pivot index, or we can say a random pivot index. Now I'm going to push this random pivot to the end of my array. So for that we have a swap method, and here I will pass my array, the random pivot that I have, and the last index, because I'm moving it at the end of the array. Great. So now my pivot is going to be end minus 1. So this is my pivot index now, because I moved it at the end. Now I have to find the correct position for this pivot in my array. So for that I'll have integers that will start from, I'll take an I integer which will start from the starting index. Then I'll take j, which will also start from the same index. And this loop will run till my j has reached the pivot. Cool. -1, because we don't want to iterate till the pivot. I mean, we want to iterate till the pivot. We don't want to include the pivot. We just want to go there. And whenever I find a value which is smaller than my pivot value, then I'll swap the numbers which is there in the ith and jth index, and increment the I as well, because we have to find a place for the pivot. And j will be incremented every time because we have to iterate till that part. Great. So once we reach there, our ith index, our ith index will become the pivot, because once we are out of this loop, we have found a place for ith index from where, I mean, all the elements to the right of the ith index will be bigger than I. All the element which is left of the ith index will be smaller than I. Therefore, our I is the correct position for our pivot. So we will swap it. So we will swap our ith index with our random pivot index. And yes, so we have swapped. So now our pivot, so everything to the right of our pivot is bigger than the pivot, and everything to the left is smaller than the pivot. Now we have to repeat this process again and again. So quicksort is gonna be, okay, again, so now our random pivot index is I because we have swapped it. Very important part. We are no longer pointing it to the end, we are pointing it to the new position that we have found for it. Great. So now our quicksort will be, now we'll sort the left part of the pivot. So our start will remain the same, but our end will be random pivot index -1. Awesome. Or we can give random index minus, we can do either way because now we have to sort the right side of this. So this is become random index, or if we keep it random index here, so we can do random x +1. So anyway it should work, I guess. And end is end. So this should sort the given array. Isn't it simple? Let's see. Great. In the first go. See, I'm telling you, Robert Sedgewick is an amazing person, an amazing professor, and he taught me quicksort, so I can never forget it. Let's see, let's recap what we have done so far so that it's easy, and also if we see if there's any scope for improvement, like if we can make it more efficient, we'll do that. Okay, so we got this input array, we made a copy of this array here in a new memory location. Why? Because we don't want to change the same input that we are getting. We want to perform operations on the new memory address. That is why this array. This is the start index of our array. This is the end index of our array. And we pass it to a function called quicksort. This is where the magic happens. Well, not the magic, the algorithm. And we programmers are magicians. Cool. So since we are going to do it recursively, we will first add the condition where it should stop. So when our start matches with our end, it means that our array has only one element. Let's say we only have 0, 0 because our start matches our end. So we have to return from that position. We cannot do any operation on that. Our array is already sorted. So we just return it. But for the first iteration, let's see how it works. We create a random integer. We generate a random integer between that array. And then we take that index, whatever we have generated with this random number. We make it a pivot and push it to the end of the array. So this is what we have done. We have swapped it. So we are pushing it to the end of our given array. So now you can imagine that we have an array. We have an element that is sitting at the end index of the array. Now, this is our random pivot index. Now we have to find a position for that number, the correct position. And if you recall, like correct position is that everything to the right is bigger, everything to the left is smaller. We take jth element, we'll start from the beginning and we'll compare all the elements with the random pivot that we have kept at the end. This is our random pivot index. And if the jth index, the value on the jth index is smaller than the pivot, we'll bring our ith, we'll swap that number with the ith number. We are not touching the pivot at this point. We are just using pivot for comparison basis. And as soon as we find a number which is smaller than our pivot, we'll compare what is there in the ith index with what we have in the jth index. We'll swap it. And we'll increment I by 1 so that we don't repeat the same index again. And jth index will increment on every iteration of this while loop. We are going to repeat the same process again and again. We are going to compare j with our pivot number, and if it is smaller, we swap it with the ith index, because we are looking for a place where everything bigger than the pivot is on the right and everything is smaller than the pivot is on the left. So every time we find a number which is smaller than the pivot index, we increment I, like we put that number here and we increment I. Then we find a number smaller than the pivot number, we put that here and we increment I. So at the end, I become the position for our pivot. So this is what we did. So ith will become the pivot. So we swap the ith index with the pivot. Now whatever we have kept at the end, we just swap it here. So now our pivot is in the correct position, and that's what we wanted. Now we have to repeat the process for the left half and the right half in the same manner. So we just call with the correct indices and it will do the work. It is that easy. I hope you enjoyed this part, and if not, then do comment. So yeah, let's do some improvements. Okay, so here ID is complaining that we are creating this object again and again inside this, so this can be optimized definitely. So to optimize it, we can not create so many elements, so many objects. We can just create one here, and since it is not going to change, we can make it final. Now this is optimized, and I do not see any other way to make it optimize. We can do it like currently we are using random pivot. To optimize this, we may not choose a random pivot, because with the random pivot, the chances are that we choose a very bad pivot. And if you're going to choose a bad pivot every time, let's talk about the worst case scenario. If you're going to choose the bad pivot every time, then you are going to end up with the n squared complexity, and that's the worst complexity that you can have. But usually that doesn't happen. You have to be really unlucky. I mean, the unluckiest person in the entire universe to have that kind of situation. But still, if you can find a way to choose a correct pivot every time, and the correct pivot would be the exact center of the entire array. So if you can choose that every time, you can have like n complexity. So this really depends on the pivot that you choose, and you can definitely optimize it. And there are algorithms out there which do optimize the pivot selection part. You cannot just leave it to luck. I mean, you cannot make it random, but if you're interested in that, you can definitely read about it. It's not very difficult to implement that portion of it. I do not remember the name of the algorithm, but I will definitely post it in the description below if you're interested. And from there you can optimize it further. And I don't think we made any bad choices here. I mean, everything looks correct. Cool. So I think I would love to end this video here. It has already been long, and I'm also a bit tired, so I'll just go sleep, and I hope you will sleep well too. And in the next part we will do something with these are all boring things. Heap sort, maybe we can pick heap sort, or we will create a way to compare these algorithms. So we'll write some analytics program with which we'll compare the running complexity of each of this algorithm, and we'll pass 1 lakh items to each of this algorithm. I mean, 1 lakh would be a lot for selection sort, but definitely we are going to do that. So I hope you will join me for the next video, because it's going to be interesting. So see you there. Bye bye. Ciao.